For most people, the ocean is a place of beauty, adventure, and opportunity. Yet beneath its calm surface lies one of nature's most destructive forces. In a matter of minutes, a tsunami can transform thriving coastal cities into landscapes of unimaginable devastation, carrying immense volumes of water with enough power to destroy buildings, roads, and entire communities. Throughout history, nations located along the Pacific Ring of Fire have lived with this constant threat. Among them, Japan has experienced some of the most powerful earthquakes and tsunamis ever recorded. Each disaster has left behind painful lessons, but it has also inspired remarkable advances in science and engineering. Rather than accepting these disasters as unavoidable, Japan chose a different path. Engineers, researchers, and emergency planners dedicated decades to understanding how tsunamis behave, how coastlines respond, and how infrastructure could be redesigned to reduce their impact. Every new discovery became another step toward protecting millions of lives. Today, stretching across hundreds of kilometers of coastline, Japan has built one of the most sophisticated tsunami defense systems on Earth. It is not a single wall or a single structure, but a vast network of seawalls, floodgates, offshore monitoring systems, evacuation routes, early warning technologies, and carefully planned coastal infrastructure, all designed to work together when every second matters. Long before a wave reaches the shore, an invisible network of seismic sensors beneath the earth and monitoring buoys across the Pacific Ocean constantly watch for unusual activity. Satellites, underwater instruments, and coastal observation stations collect enormous amounts of information every second, allowing scientists to detect potential threats almost immediately after a powerful earthquake occurs. The collected data is transmitted within moments to advanced monitoring centers, where sophisticated computer models estimate how a tsunami may travel across the ocean. Engineers analyze wave height, speed, direction, arrival times, and potential coastal impact with extraordinary precision, allowing emergency authorities to issue warnings while the tsunami may still be hundreds of kilometers away. But technology alone cannot stop the ocean. Once a warning is issued, physical protection becomes the next critical line of defense. Along vulnerable coastlines, massive reinforced concrete seawalls stand between the Pacific Ocean and nearby communities. Some rise several stories high, carefully engineered to absorb and redirect enormous wave energy while reducing flooding behind the barrier. Where geography allows, engineers have added offshore breakwaters designed to weaken incoming waves before they even reach the coastline. These structures reduce wave energy, decreasing the force that eventually reaches seawalls and coastal communities. Together, they form multiple layers of protection rather than relying on a single defensive structure. Critical river entrances are protected by enormous steel floodgates, capable of closing rapidly during emergencies. These gates prevent tsunami water from traveling inland through rivers and canals, protecting areas that might otherwise remain vulnerable even if coastal barriers perform as intended. Modern coastal protection also depends on carefully planned evacuation systems. Elevated roads, escape towers, emergency shelters, and clearly designed evacuation routes provide residents with fast access to higher ground whenever warnings are issued. Years of public education and regular emergency drills ensure that communities know exactly how to respond when every minute becomes critical. Behind every visible structure lies decades of scientific research, engineering innovation, and continuous improvement. Every earthquake has provided valuable information. Every tsunami has revealed new challenges. Instead of repeating past mistakes, Japan has transformed each lesson into stronger designs, smarter technologies, and more effective disaster preparation. The result is far more than a collection of concrete walls and monitoring equipment. It is a living engineering system that combines science, technology, infrastructure, and human preparedness into one coordinated effort with a single purpose: to reduce risk, protect communities, and save lives before disaster strikes. As climate change, rising sea levels, and expanding coastal populations create new challenges around the world. The importance of resilient coastal engineering continues to grow. Japan's experience demonstrates that while natural disasters cannot always be prevented, their consequences can be significantly reduced through knowledge, planning, and long-term investment. This is the story of how one nation transformed tragedy into innovation, and how decades of engineering excellence created one of humanity's most advanced defenses against one of nature's most powerful forces. Designing a tsunami defense system begins long before the first concrete foundation is poured. Every coastline presents its own challenges, shaped by underwater geography, wave behavior, tidal patterns, and the geological forces hidden beneath the Earth's surface. Before construction can even begin, years of scientific surveys are carried out to understand exactly how future tsunami waves may interact with the landscape. Teams of marine geologists, oceanographers, and structural engineers collect enormous amounts of information using sonar mapping, seismic imaging, and underwater inspections. Every contour of the seabed is analyzed because even small variations beneath the ocean can dramatically influence how a tsunami grows, slows, or changes direction before reaching land. With this knowledge, engineers create highly detailed computer simulations capable of reproducing thousands of possible tsunami scenarios. Different earthquake magnitudes, wave heights, arrival times, and weather conditions are tested repeatedly, allowing designers to evaluate how every section of the coastline might respond during an extreme event. The goal is not simply to build the tallest seawall. Every structure must balance safety, environmental impact, construction cost, maintenance requirements, and the needs of nearby communities. A defense that works perfectly in one location may be completely unsuitable only a few kilometers away. Once the designs are finalized, construction begins with preparing an exceptionally strong foundation. Massive excavation equipment removes unstable material before layers of compacted, rock and reinforced foundations are installed to create a stable platform capable of supporting thousands of tons of concrete while resisting powerful earthquake forces. Special marine concrete is then poured using carefully controlled construction techniques. Unlike ordinary concrete, these structures are engineered to withstand continuous exposure to seawater, extreme weather, and decades of relentless wave action. High-strength reinforcement steel is embedded throughout the structure to increase durability and prevent catastrophic failure during severe loading conditions. Every section of the seawall is built with remarkable precision. Expansion joints allow controlled movement during earthquakes. Drainage systems reduce water pressure behind the walls, and carefully engineered surfaces help redirect the tremendous energy carried by incoming waves. Even seemingly small design details play an important role in the overall performance of the structure. Meanwhile, construction extends beyond the shoreline itself. Offshore breakwaters are assembled using enormous concrete units and carefully positioned armor rocks that absorb wave energy before it reaches land. Their placement is calculated with extraordinary accuracy to maximize protection, while minimizing disruption to marine ecosystems and coastal navigation. Along rivers and estuaries, giant steel floodgates are installed to prevent tsunami water from pushing inland through natural waterways. These massive mechanical systems are designed to close rapidly during emergencies, while remaining reliable after years of continuous operation in harsh marine environments. Throughout construction, engineers conduct constant inspections to ensure every component meets strict safety standards. Concrete strength is tested, reinforcement placement is verified, and precision instruments monitor even the smallest structural movement. Every stage undergoes rigorous quality control because a single weakness could compromise the performance of the entire defense system. Building such infrastructure requires far more than engineering expertise alone. Thousands of workers, heavy machinery operators, marine construction specialists, environmental scientists, and logistics teams coordinate their efforts over many years. Every completed section represents countless hours of planning, precision, and teamwork. Yet despite the enormous scale of these projects, engineers understand that no physical barrier can provide complete protection on its own. True resilience comes from combining strong infrastructure with early warning systems, emergency planning, scientific research, and well-prepared communities capable of responding quickly when disaster strikes. The result is a carefully integrated defense network where every seawall, floodgate, offshore barrier, monitoring station, and evacuation route works together as part of a single coordinated system. It is this combination of engineering excellence, scientific understanding, and long-term planning that has transformed Japan into one of the world's leading examples of modern tsunami resilience. The story of Japan's tsunami defense system is not simply the story of concrete walls, steel floodgates, or sophisticated monitoring equipment. It is the story of a nation that refused to let repeated tragedy define its future. Instead, every disaster became an opportunity to learn, improve, and build something stronger than before. Today, engineers from across the world continue to study the methods developed along Japan's coastline. Universities, research institutions, and international engineering organizations regularly exchange knowledge, sharing decades of scientific experience that can help protect vulnerable communities far beyond the Pacific Ocean. Every successful project begins with a simple understanding. No coastline is exactly the same. Local geography, ocean depth, climate, and population all influence how coastal defenses should be designed. Rather than copying one solution everywhere, engineers adapt proven principles to meet the unique challenges of each region. At the same time, the next generation of engineers is preparing for challenges that previous generations could scarcely imagine. Rising sea levels, expanding coastal cities, and increasingly unpredictable weather patterns require entirely new ways of thinking about resilience. Tomorrow's infrastructure must not only be strong, it must also be flexible, intelligent, and capable of adapting as conditions continue to change. Artificial intelligence, satellite observation, autonomous inspection drones, underwater robotics, and real-time sensor networks are already transforming the way coastal infrastructure is monitored and maintained. Instead of reacting only after damage occurs, future systems will identify potential weaknesses long before they become serious risks. Sustainability has also become a central part of modern engineering. Coastal forests, restored wetlands, living shorelines, and renewable energy systems are increasingly integrated with traditional infrastructure, creating protection that works with natural ecosystems rather than against them. This balanced approach helps reduce environmental impact while strengthening long-term resilience. Yet even the world's most advanced technology has its limits. The greatest defense against natural disasters has never been concrete alone. It is preparation. Communities that understand the risks, practice evacuation procedures, maintain emergency plans, and trust scientific guidance are always better equipped to face uncertainty when disaster strikes. Protecting coastlines is therefore a shared responsibility. Engineers design stronger infrastructure, scientists improve forecasting models, emergency responders prepare for rapid action, governments invest in resilient development, educators teach future generations, and local communities remain the final and most important link in the entire system. Japan's experience proves that resilience is built over decades, not overnight. Every inspection, every research project, every emergency drill, and every engineering improvement adds another layer of protection. Progress is achieved through countless small advances that together create extraordinary results. As humanity continues to build more cities along the world's coastlines, the importance of resilient engineering will only continue to grow. The lessons learned here extend far beyond a single country. They offer a practical blueprint for how science, innovation, and long-term planning can help societies live more safely beside one of Earth's most powerful natural forces. Perhaps the most important lesson is not about defeating nature, because nature can never truly be conquered.